from Make Math Easy, and today we're going to talk about a different kind of object. Unlike solar system objects, this object doesn't have a place in our solar system, because if it were in our solar system, the results wouldn't be so pretty. But these kinds of objects, despite sometimes being smaller than even a few neutron stars, unlike neutron stars, black holes have much, much higher gravity and much, much more luminosity. So what's up with all the gravity? The black holes have so much gravity, actually, that the escape velocity is faster than light. There's a single point called the event horizon. Given that the speed of light travels at 299,792.458 kilometers every second, or 299,792,458 meters every second, to make it even clearer, that fast, imagine something having to go that fast to escape a black hole. It's impossible. We don't have the technology to go that faster than that. And turns out that light doesn't have its own necessary speed. So black holes are a place basically where nothing at all, not even light, can escape. Well, actually the only things that can escape are mass, radiation, and tachyons. By the way, if you're not knowing, tachyons can go faster than light, but they're less than a yoctometer wide. But either way, turns out that despite these objects escaping, light can't escape. Hence the name black, which means that we can't see them due to the sucking of light, and hole, since it's like a hole. Note that wormholes are a different kind of black holes, that at one end is a black hole, but at the other is a white hole. However, we think black holes might break the wormhole crunch, because maybe you could fall back into a white hole, but then you couldn't come out the black hole. You'd have to get sucked right back in, like an endless loop. Unless the black hole somehow shoots you faster than the speed of light. So, black holes have a very high gravity. Turns out, they're so dense that a warm solar mass black hole is this big. And that, my friends, is less than 1,000th of the sun's size. That is smaller than Sirius. Hell, that's even smaller than the smallest black hole we've discovered. However, there is a hypothetical kind of black hole called the micro black hole. It's only about 5.7 times 10 to the negative 35 meters, or about 5.7 times 10 to the negative 11 yoctometers. It's really, really tiny. And what's up with that tiny? Something that tiny would radiate in like orders of billions of milliseconds. It's because it would have a very, 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 very low mass. Very low. Okay, let's kick it up one more notch and make it an Earth-sized black hole. It's just the size of a penny. So the size of that is what you call the Schwarzschild radius, which is the radius that an object must be compressed, assuming that its mass doesn't change, in order for it to become a black hole. For the Sun, it'd be this big. For the Earth, about 1.8 centimeters. For Jupiter, about 5 meters, which is still quite high. And for a star about this massive R136A1, about 1,000 kilometers. That's really big. However, that's because R136A1 is the most massive star. So, if you shrunk a star to the size of a black hole, the biggest one of those black holes would be if you shrunk R136A1 to a black hole, assuming that its mass did not change. See, mass, density, and volume have a relationship. Mass divided by volume equals density. Now, actually, that's why the base units of density is grams per cubic centimeter. So there are several kinds of black holes. So we'll talk about each one. First are stellar black holes. Stellar black holes the micro black holes are much bigger, obviously. Now, these black holes form when stars end their lives. When stars 8 times as massive as the sun or higher, actually, much more massive, the core collapses in on itself as no force is no longer produced to balance the inward force trying to collapse and the pressure for the gravity is trying to collapse the star. However, the pressure from the star's fusion keeps it open. It's like trying to open a wormhole with exotic matter or stuff with negative mass. However, propping open the star is limited due to nuclear fusion. When nuclear fusion stops, the pressure force is gone and gravity wins to collapse the star. As it collapses, the core gets smaller and smaller and turns into a super dense ball of neutrons. Now, of course, the core eventually turns into a super dense ball of neutrons in some cases. But then the outer layers also collapse inward and bounce off the core in a huge explosion that we refer to as a supernova. The supernova is followed by something that depends on the mass of the core. If the core is between like 1 solar mass and 3 solar masses, then the core will start to collapse and collapse and collapse, but then stop at one point as the core turns into a super dense ball of neutrons. That is the second most densest object in the entire universe. Those are called neutron stars. And they are not only extremely dense, but extremely hot. Their temperature on the surface is more than half the temperature of the sun's core. 8 million degrees Kelvin. So hydrogen bombs are 400 million degrees Kelvin, but literally the core of a neutron star is like twice the heat. But anyway, neutron stars are really, really hot, but they don't always occur. If it's higher than 3 solar masses, it collapses further than if it became a neutron star and collapses and collapses and collapses until the core reaches its Schwarzschild radius and turns into a black hole. In which case, neutron stars do not occur. Okay, back to black holes. Now, stellar-mass black holes have between like 3 times the solar mass. Here are 2 of them. The smallest black hole we know is IGRJ 17091-3624. It is the smallest black hole we know. It is 17.8 kilometers wide. Like, really tiny. And also not as massive as other black holes, like only 3.5 solar masses. Another example is XTJ 1650-500. It's about 24 kilometers wide, and despite being this big compared to IGR, it's actually still quite small. Note that the following black holes are being listed by size. Now there are some additional black holes that are in the in-between range of 2 black holes, so I will mention these kind of black holes. Our next black hole is Cygnus X1, which is this big compared to the previous 2 black holes. It's about 100.3 kilometers, which makes it just over 2 marathons wide. But it's just not as big as some other black hole out there. So next black hole up is Messier 15 black hole. If you learned about Messier and his catalog of objects, you might know that he didn't catalog any stars or black holes. If Messier didn't catalog any black holes, what do I mean when I say Messier 15? Sometimes astronomers just refer to black holes like that because they're actually talking about the black holes at the center of the object that was the Messier object that he cataloged. So for example, Messier 15 would be the black hole at the center of Messier 15. Now the Messier 15 black hole is quite big. If you just zoom out until you get to it, it's about 210 kilometers. Next black hole on the list is the Messier 115 black hole, or the black hole at the center of Messier 115. It's actually about 354 kilometers. Now, that's still a small one compared to other black holes, like SAG 3 black hole. There's another one, like Arp Maldror 1, or NGC 121. Now, as you might realize, these are in the thousands of kilometers, unlike stars which skip the hundreds of kilometers, and we saw black holes in the hundreds of kilometers, and you'd be like, Cozy, what is going on? It's because black holes have all kinds of sizes. We don't know how the bigger ones formed, but we think it's when more than one stellar black hole merged together. Colliding two black holes just makes a mega black hole. We think this might be how supermassive, intermediate, and ultramassive black holes formed. Actually, we've already reached intermediate black holes. Intermediate black holes are on the order of approximately thousands of kilometers wide, but intermediate black holes bigger than NGC 121 do indeed exist, like Messier 9 black hole, or HLX1, or G-Series 13e. So, and for reference, let's just add the Earth, and actually I forgot the Moon, so I'll just add it inside, because who can forget the Moon? Now, I just realized that the Moon is actually bigger than lots of black holes, and of course it's bigger than stellar black holes, but the Moon and the Earth have very small Schwarzschild radiuses. Now, wait a minute. If we are at Earth, there are certainly black holes bigger than Earth, right? Correct! If anyone out there has been thinking that black holes can get bigger than Earth, that is absolutely true. Most black holes we've discovered are actually indeed bigger than Earth. Actually, most of them are bigger than our even sun. Big. So, here are some black holes bigger. Messier 54 black hole. Neptune first, because it's for reference. Mail 2 black hole, Jupiter, for reference. Omega Centauri black hole. We can see lots of these are inside clusters and that stuff, and that kind of makes sense. Lots of supermassive black holes are at the center of galaxies. Actually, here are some examples. So this is the Sun, this is Andromeda G21. This is another black hole. Now, this is NGC 1234 black hole, which is interesting. And now here's another black hole. Sagittarius A black hole. Aha! Wait a minute. Sagittarius, there's no such thing as Sagittarius A as a cluster. Sagittarius A actually has an asterisk as its name, as you might notice, but it's at the center of the Milky Way. This is, and you might be thinking, we're gonna get eaten. Just don't make me any more scared. Just stop the video. No. Don't just close the laptop you're using on me, because we are safe from this black hole. Turns out, we are lucky to live in a time where we have lots of time to prepare for a black hole invasion. Now wait a minute. Actually, are black holes bigger than Sagittarius A? Yes, lots of black holes are bigger than Sagittarius A, like the Mercurian 335 black hole, Mercurian 110 black hole, or even Andromeda Galaxy black hole. Now, hold on a second. There's also some more, like Samuro Galaxy black hole. Now, at this, we enter a completely new phase of black hole. There's still something to consider. Now we enter ultramassive black holes. Black holes bigger than lots and lots of black holes. Ultramassive black holes are huge, like Hercules A, which we're now in the tens of billions of kilometers, Messier 87 black hole. Hercules A has an asterisk, but the actual galaxy inside is the same but without an asterisk, which is how you can tell the difference between the two. After Messier 87, there are some more, like SID 947 black hole, OJ 287 primary, this black hole at the center of the Phoenix cluster, the black hole at the center of NGC 4889, a galaxy very big, not a black hole, and then there's some more, like this black hole, or even another one, H1821 plus 643. Or even this one, which has a super long name that I'm not going to read out. Or S50014 plus 8. At this stage, we've gotten way bigger than lots of things. This is the basically fourth largest black hole. Next is Holmberg 15A black hole, IC1101 black hole, then Tone 618, and then get ready for the big zoom out. This is the biggest black hole we know. Diameter of 1.2 trillion kilometers and a mass of 196 billion suns. Imagine containing as much matter as 196 billion suns in something almost an eighth of a light year. Super big. And really, these sizes are humongous. Actually, we can verify that it is 196 solar masses at the end of the Wikipedia list of most massive black holes. And, actually it ends at Tone 618. But there are lots of things you can search up about this black hole, and you do indeed get that it is 196 billion solar masses. So, either way, you can still confirm it even without using this list. But if black holes get that big, our thing is, have we discovered any black holes bigger? Not really. But the Schwarzschild radius of several objects are bigger than that. This is the Schwarzschild radius of the Milky Way, or the diameter of the Milky Way has to be crushed to become a black hole. Here's another one that is so big that we'll just add a light year here for purposes. Even though it's useless because when we zoom back out, you can't see all those smaller black holes because it's too big. Waiting for the results, and aha! Here it is! A black hole with the mass of the universe would have to be 27.6 billion light years. That is almost the size of the entire universe that we can see, or the diameter that we can see the entire universe of. If you remember watching my video about how far back we can see time, which if you haven't, I recommend you should watch before continuing, I said the farthest you can see is 13.8 billion light years. So the visible universe's radius is 13.8 billion light years, making its diameter just a bit bigger than this black hole's humongous radius. It's so big that this is the universe for comparison. Things really get huge with these black holes, and I hope all this stuff about learning about black holes and all that stuff helps you understand just how difficult it is to comprehend such sizes. So actually, what happens if you enter a black hole? If you enter a black hole, you'll first start by getting stretched very, very much. And being stretched very, very much is not fun, of course. Turns out, if this makes you laugh, it made me laugh the first time. Well, it made me feel kind of funny the first time I learned this, but we actually call this, and I am not kidding, we call this spaghettification. That's like ridiculous. But it really is true, because you get stretched into such a shape that you look like a spaghetti. So if you were outside, you'd get stretched into a spaghetti, and then stop moving, and then start fading and fading and fading away until you enter what's called the event horizon, or the point of no return. This is exactly when space itself is moving at the speed of light into the black hole. So we assume that the event horizon is a point of no return, where nothing, at that point, nothing, not even light, can escape. The size of this is massive, and really, black holes have an outline. By the way, have we ever imaged a real black hole? The answer? Yes! This is an image of the Messier 87 black hole, or the black hole at the center of Messier 87. It was the first black hole to be imaged, ever. And this was a huge achievement, actually imaging a black hole. This confirms black holes do exist. So to conclude, black holes range from tiny things the size of cities to as large as tons of solar system orbits. Their mass also determines their size. black hole is about this big, and a Jupiter mass black hole is this big, and an Earth mass black hole is approximately the size of the US penny. Now, black holes form when stars die in a supernova explosion, when the outer layers bounce off, and the core needs to be about 3 solar masses or higher to achieve this, which is why no black holes are smaller than 3 solar masses, which means the lower limit for the size of a black hole is approximately this big if you do the math with me. So therefore, black holes are huge, and I just hope it goes some way to show you that neutron stars and black holes are just the extremities. We are lucky that our sun is the right mass to not explode and cause a black hole. Anyway, that's it for Make Math Easy, and I remind you to stay curious in math and science.